Hello, my calculus rock stars, and welcome to another edition of Miss Bowman is Losing Her Mind and is going to talk to you for 45 minutes to an hour. We are going to be doing Unit 4, or not Unit 4, oh my goodness, it's Unit 3. You think the fifth one I've done today, I would have the right unit. Unit 3, Day 5 notes. These are going to be the last of our derivative rules. Whoop, whoop. We're going to go through this one. This is a bit of a long one, so make sure you've set aside some time. Pause it, take breaks, all the good things that come with asynchronous ability, take them. We are going to be doing the inverse trig functions today, as well as just talking about inverse functions in general. Okay, so how do we find the derivative of inverse trig functions? How do we find the slope of an inverse function? And how does that slope relate to its regular one? So we're going to go through and just kind of review inverse trig functions to begin with, and then we'll get into deriving the derivative rules. And once we've derived them once, you don't have to derive them again. It's just a proof. You can just use the rule. I will chain rulify all the rules so that we have it, and then we'll go through and do that. So let's get on into today's lecture, inverse trig functions. So if you remember, the inverse trig functions, okay, are commands. Feeling calligraphy pen today. Let's see. Commands that calculate angles. So they're the angle finding commands. They're saying, given a side ratio, what is the angle? Okay, you're either going to see them written in inverse notation, so with that little -1, or as arcs. Okay, so like arc sine, arc cosine, arc tangent, those are the inverse functions. Okay, so let's see how much you remember. Take a second, pause me, and evaluate the following for the inverse function f of x equals inverse sine x. Again, or you'll also see that written as arc sine of x in those textbooks that don't like using the little -1, just because we tend to think -1 is an exponent as opposed to a notation. See what you can remember from these. Pause me and unpause me. Okay, so for inverse sine, one of the things that you need to realize is that when you have the inverse trig function, if it is a function and you think about like the sine graph itself, it is not a one-to-one function. So we actually chop the sine graph off to create the inverse sine function. And so it would have a restricted range. So when we're talking about evaluating it as an inverse sine function, it's going to have a range that's restricted between -π/2 and π/2. So these are the only angles that are possible as outputs for the inverse sine function. Okay, so if I'm looking for the sine of 1/2, I'm saying what angle gives me a sine of 1/2. So if I think about 1/2, what reference angle is that? That is the 30, 60, 90. So this is the 30 degrees. That would be π/6. And then again, you're only going to have angles between -π/6 and π/6. So we're only in quadrant 1 here. So -√3/2 means we're going to be in quadrant 4 down here. So if I'm thinking about that one, that's going to be -π/3. Inverse sine of -1, that's a quadrantal. Sine is -1 down here, which going forward would be 3π/2. Going backwards, since that's what we're doing, would be -π/2. So again, we're going from -90 to 90 to make it continuous, a continuous range, as opposed to doing like 0 to 90 and then 270 to 360. We're just going to say -90 to +90 or -π/2 to +π/2. Okay, now this one is fun. Find the cosine of the angle that gives me a sine equal to 5/13. So if I think about the inverse sine over 5/13, that's saying find some angle that gives me a sine of 5/13, and then find the cosine of that angle. So if I want that, then I'd have to find the missing side, which is a 5, 12, 13, and the cosine of the angle that gives me a sine of 5/13 would be 12/13. Now let's go ahead and sketch, just so we have it down, what the inverse sine function looks like. Again, the inverse sine function has been chopped. It has a closed domain. So if we think about sine of x, if this is the inverse, the domain and range have been switched. So the domain would go from negative 1 to 1. The range is going to go from negative pi over 2 to pi over 2. Okay, we're going to start negative 1 comma negative pi over 2, 0, 0, 1 comma pi over 2. And the graph looks something like this. The domain is negative 1 to 1 inclusive. The range is negative pi over 2 to pi over 2 inclusive. Okay. So that's your little inverse sine. So now let's do inverse cosine. The inverse cosine function, again, it's restrictions here to get every value of cosine. Since it's the x, is going to go from 0 to pi. So the outputs of inverse cosine are only going to be quadrant 1 and quadrant 2 of the unit circle, 0 to pi. So cosine is equal to 1 at an angle of 0. Cosine is equal to negative 1/2 at an angle of, let's see, it'd be in quadrant, so cosine would be 1, 2, root 3, so that is 60, so that's going to be pi over 3, but since we're in quadrant 2, it's going to be 2 pi over 3. Okay, inverse cosine of root 3 over 2 is going to be pi over 6. And then here again, let's go ahead and figure this one out. So we have an angle, since that's what inverse cosine finds, that gives me a cosine equal to negative 2 over 3. So if the cosine is equal to negative 2 over 3, I know I'm in quadrant 2 because that's where cosine is evaluated. And since it's negative, it's got to be quadrant 2. I'm going to use Pythagorean theorem here to find the missing side. So 9 minus 4 would be root 5. It's positive because we're in quadrant 2. And then the sine of that same angle would be root 5 over 3. Okay, let's go ahead and sketch this inverse cosine graph. So this one still goes from negative 1 to 1 as my domain because that's the range of cosine. The range of inverse cosine is going to be the domain we restricted cosine to, which was 0 to pi. So we got 0 to pi for the range. At negative 1, it's pi. At 1, it's 0. And then we have pi or half a pi. And the graph would look something like this. Now, a couple of things, since we're going to be talking about the derivatives of these. Notice how the inverse sine graph is increasing the whole time. That should tell me that the derivative has a positive value, whereas the inverse cosine graph is decreasing over its interval, which means that this derivative should have a negative value the whole time. Okay, now inverse tangent, pause me, think about arctan or inverse tan, and then unpause me. Okay, inverse tan, again, its restrictions are going to be negative 90 to 90 or negative pi over 2 to pi over 2. Those are the only possible angles that we can output. So if I'm thinking about negative root 3, that tells me that my opposite is negative root 3. My adjacent is 1. Oh, that must be the 1, 2, root 3. That is a 60-degree angle, so that would be pi over 3, but quadrant 4 would be negative. Root 3 over 3, that's the pi over 6 family. Tangent, inverse tangent of negative 1 is going to be the pi over 4 family, but since it's negative, it's got to be quadrant 4. And then the tanverse, okay, so now I'm going to draw a right triangle. Find the tangent of the angle that gives me a tangent equal to 3. Okay, well, if I find the angle, I know the opposite over the adjacent is 3, so if I find the tangent of that angle, it's actually 3. Tangent and inverse tangent are inverse operations, so that should just cancel out to give you 3. And then if we graph it, we got horizontal asymptotes of pi over 2 and negative pi over 2. And the graph looks like this. Okay, the domain is all reals. The range is negative pi over 2 to pi over 2, non-inclusive. Okay, so there's actually horizontal asymptotes. Notice this graph is increasing the whole time, which means the derivative graph should be positive the whole time. Now, I'm not going to do the other 3 inverse trig functions because we don't really deal with them too much. In fact, I'm just going to teach you a way to do them in your calculator. But now what we are going to do is take those 3 inverse functions that we did do and find the derivative of each. Okay, so we're going to do the proof for the derivative of inverse sine. Our goal is to figure out what is the derivative of inverse sine. Okay, that's our goal. Now to do this proof, what we're going to do is we are going to use an identity. So our identity is the fact that sine of the inverse sine of x is equal to x. Okay, that's pretty cool. So let's see what we can do here. Well, I'm going to take the derivative of both sides of the equation. If those equations are equal, then their derivatives should be equal. Now on the right side, the derivative of x is 1. God, I love when that happens. On the left side, if you notice here, team, we have a chain rule. Inverse sine is plugged into sine. So what I'm going to do is take the derivative of the outside, which would be cosine, keep it in terms of the inside, times the derivative of the inside, which I don't know, but I'm going to call it the derivative of inverse sine of x. That's actually the part that I want. So I know the product of these two expressions should equal 1, which means the derivative of inverse sine is 1 over the cosine of the inverse sine of x. Okay, now you are probably like, Ms. Bowman, that is the nastiest derivative I've ever seen. And I would 100% agree with you. So what I want to do is I want to find an easier way to write this because like, why in the world would I want to do this? So I'm going to channel what we did in kind of those first examples and think to myself, how could I simplify this expression? Okay, and I'm going to use a right triangle to help me. Now, this is saying find cosine of an angle that gives me a sine equal to x. So whatever the angle is, I'm going to find the cosine of that angle, but I know that angle gives me a sine equal to x. Well, x is just x over 1, so I'm going to think of it as x over 1. So I know the sine of this angle equals x over 1, so I know my opposite is x, and my hypotenuse is 1. Which means I can find the missing side using Pythagorean theorem. So this would be the square root of 1 minus x squared. And then I can find the cosine of that angle. The cosine of that angle would just be adjacent over hypotenuse, which would just be this. So I can replace that expression with the square root of 1 minus x squared. Welcome to your first inverse trig derivative. So the derivative of inverse sine of u, and I'm going to go ahead and chain rulify this, is 1 over the square root of 1 minus u squared times du. Now, where does that du come from? Again, it's from the chain. And there is your first inverse trig derivative. It is weird to me because with the trig definitions, I'm always like, okay, so trig gives me trig, and that makes sense. But inverse trig does not give me inverse trig. I mean, technically it does, but then we can use some tricks to rearrange it, and then we end up with this weird like square root expression that has no trig involved whatsoever. Go ahead and try this example on your own, and then unpause me and we're going to go through it. Okay, so in this case, inverse sine of 3x, the 3x here is the same thing as like the u in my chain rule. So I know u is equal to 3x and du is equal to 3. And now I'm just going to put this in the rule. So the derivative of inverse sine of u is 1 over the square root of 1 minus u, which is 3x squared times 3. And if I clean it up, it would just be 3 over the square root of 1 minus 9x squared. And there's my derivative. Don't have to do much. Can't really do anything else. And that's it. All right, 1 down, 5 to go. So next, let's look at the inverse cosine. Now, I'm going to use an identity to figure out the derivative of inverse cosine. I am not going to use the same identity that we did for inverse sine, although you totally 100% could. And if you did, like, more power to you. Actually, you know what? Let's do it. So let's prove it using that identity. There's a different one in the completed notes online, but we're going to use the identity that this expression is equal to just x. Okay, so we're going to start by taking the derivative of both sides. This is a chain. We have a function and one function plugged into another, so I'm going to use chain rule. The derivative of cosine is negative sine. Keep the inside the same, times the derivative of the inside. Well, I don't know what that derivative is. I'm just going to say whatever, it's the derivative of inverse cosine of x. And then the derivative of x is just 1, and I end up with an expression there. Now, if this is the piece I want to figure out, I'm going to isolate that piece, and it tells me the derivative of inverse cosine of x is 1 over negative sine of the inverse cosine of x. Okay. What I might automatically do is just move that negative on top, just because I don't like it with that sign. But now I'm going to use the same idea to simplify this like trig, inverse trig expression by thinking of my right triangle. So I'm trying to find sine of an angle. I want to calculate the sine of an angle, and that angle gives me a cosine equal to x. And x is just x over 1. So if the cosine is equal to x, that means the adjacent is x and the hypotenuse is 1. And that means that this missing leg would be the square root of 1 minus x squared using Pythagorean theorem. So now if I want to find the sine of that angle, it's just opposite. So the sine of theta here is just opposite over hypotenuse, which tells me that my derivative is just negative 1 over the square root of 1 minus x squared. So the derivative of inverse cosine is the exact same as the derivative of inverse sine, except that it is negative. It starts with the c. It follows the same patterns that, all the trig derivatives did. So let's chain rulify this. The derivative of the inverse cosine of u is negative 1 over the square root of 1 minus u squared times du. Okay. So there is derivative rule number 2 of the day. 2 of 6. Well, 2 of 7. Okay. Now let's just go ahead and prove inverse tangent. All right, team, guess how we're going to start it? It's going to be awesome. We're going to start it with an identity. So the identity we're going to use here is that, I'm feeling like I'm trying to do like a lilac color. The tangent of the inverse tangent is equal to x. Now here's my challenge to you. Prove it on your own. Pause me and see if you can come up with the proof, and then we'll talk about it in case you can't. While I take a sip of water. Okay, let's see if you got the first step right. I'm going to take the derivative of this equation. I'm going to use chain rule here on the left. So the derivative of tangent is secant squared of the inside that doesn't change in chain rule times the derivative of the inside, which I don't know, so I'm just writing it's the derivative of the inside, equals 1. So d dx of inverse tan of x is equal to 1 over the secant squared of inverse tan x. Okay, so that's my derivative, but it's ugly, and I want to make it clean because I have a trig and an inverse trig, and it's being squared, but we'll deal with that in a little bit. So let's do some right triangle work. So we're trying to find the secant of an angle that gives me a tangent equal to x. So I know opposite has to be x, the adjacent has to be 1, because now that tangent of theta would be x over 1. The missing side then would be the square root of 1 plus x squared if I use Pythag. And so my secant of theta would be hypotenuse over adjacent. And then if I want to go ahead and square that, the square root of 1 plus x squared is just the 1 plus x squared. And there's your derivative. Hopefully you got somewhere close to that. Now, also hopefully, you chain rule defied it. So the derivative of the inverse tangent of u is 1 over 1 plus u squared, or you could do u squared plus 1. Order does not matter in addition, times du. And there is your derivative. I got things popping up on my screen. I'm really just trying to highlight this for us. There we go. We'll do just like a baby pink. And there is the inverse tangent derivative. So see if you can use this rule and try number 2. Okay. So if I was going to find dy dx here, it's going to be 1 over 1 plus u, which is the square root of x squared, times the derivative of u. Now this is x to the half, guys. This was actually like a 2 chains. So the derivative of x to the half is 1/2. Let me try to write things. 1/2 x to the negative half. Now, if I'm going to clean this up, this is just 1 over 1 plus x. This is 1 over 2 root x. And then I would just make it one fraction. 1 over 2 root x times the quantity 1 plus x. You could also distribute that in. I'm going to leave it as just 2 things being multiplied on the bottom. And there's my derivative function. Okay. Cotangent. Let's do number 4, inverse cotangent. Now I'm going to use a different identity here to prove this one. So let's use the cofunction identity. So the cofunction identity is one we haven't seen since Math 4, but it's always good to throw these identities out there. The cofunction is the fact that every trig function has like a partner, and it's just like a rotation and a reflection of that. So the cofunction identity for cotangent is the fact that it's just pi over 2 minus the inverse tangent. So that's the cofunction identity. Just a nice little nifty identity. And the reason why I'm going to do this is because I just did this derivative, and so I can just take the derivative of this equation, and that would give me the derivative of inverse cotangent, which is what I'm trying to derive, is equal to, now here it's interesting because pi over 2 is just a number, its derivative is 0, minus the inverse tangent of x is 1 over 1 plus x squared, which just leaves me with negative 1 over 1 plus x squared. Welcome to the cotangent. So the derivative of cotangent of u, if I want to chain rule it, is just negative 1 over 1 plus u squared times du. Now, hopefully, good mathematicians look for patterns. So hopefully you are seeing a pattern here. Okay, sine and cosine are the same, except cosine is negative. Tangent and cotangent is the same, except for cotangent is negative, which leads me to the last two, secant and cosecant. Now, if we prove secant, you know the cosecant is going to be the same thing, except it's the negative version. So I'm just going to do inverse secant, and then we're going to do a practice problem with inverse secant, and then we will do, we'll write down the inverse cosecant one. And then we'll talk about calculator use and inverse functions. Okay, so this one. We are going to start with a handy dandy identity. Whoa, I'm still writing with highlighter. Hope you guys are enjoying my calligraphy pen. I really dig it more than the regular pen. I'm just feeling all these different colors today. This is the 5th one of these I've recorded in a row, so I'm trying to spice it up. All right. Ooh, look at that maroon. This is good October 12th color, which is the day I'm filming this. All right, so secant of inverse secant of x equals x. Let's use that identity, and let's do it. Now, secant this is a challenge. If you can pause me and do this one on your own, I'm like hella impressed. Okay, team? Like, this is a tough one, but I think you can do it. So try it on your own, see how far you get, and then, whenever you get stuck, unpause me, and then we'll go through the rest. And if you get all the way through, like, kudos, okay? So hopefully you're pausing me, trying it on your own, and then unpause me. All right, let's see how far you got. I'm going to take the derivative of this equation. Now, the derivative of the right side is just 1. That's easy. On this side, we're still using our chain rule, but it's secant, guys. And secant self-tans. So the derivative of secant is secant of the angle times tangent of the angle. So that's just the derivative of secant times the derivative of the inside function, which I don't know, and I'm just going to write it as an expression that says it's the derivative of inverse secant equals 1. So then we end up with that the derivative of the inverse secant is 1 over the secant inverse secant of x times the tangent of the inverse secant of x. Okay, now we're going to right triangle it. So we have some angle where the secant of that angle is equal to x, which means it's a hypotenuse over the adjacent, and the missing side would be 1 minus square root of 1 minus x squared using Pythagorean theorem. Or no, I totally messed that up. It would be the square root of x squared minus 1. That's a big difference because x is the hypotenuse here. Okay, so if I want to do the secant of that angle, it would just be x over 1. Now, there is one little catch here that you probably didn't do, even if you figured out that this was just x, and that's the fact that we need to ensure positivity here because we want to make it match the function, and inverse secant is an increasing function. It like increases the whole time. I don't want to draw it, so we just need to ensure positivity there. Okay, and then the tangent of that angle is just going to be the square root of x squared minus 1. And that is your derivative formula. So the derivative of inverse secant of u is 1 over the absolute value of u times the square root of u squared minus 1 times du. Okay, put a star by this one, again, because there is an absolute value. That absolute value is there to ensure positivity. It is a trick that comes with this one, but this would be your derivative. All right, so try this example on your own. Pause me, and then knock it out, and then I'm going to do it. Okay, so in this case, if we're going to do this one, just having all sorts of color fun here. Maybe I'm feeling this light green. Let's see how this looks. Okay, we're trying to find dy ds and dy ds here. So, dy ds. Now in this case, here's my u. So if I'm using my chain rule form, it's going to be 1 over the absolute value of u times the square root of u squared minus 1 all times du. So that gives me 5 over the absolute value of 5s, the square root of 25s squared minus 1. Now, can you cancel out these 5s? Yes. But you need to keep that s in the absolute value. And there's your derivative. Okay. Now, inverse cosecant. And again, I'm not going to go ahead. We've derived, we have done derivations and proven 5 out of 6 of these. I'm okay with us just saying at this point that the derivative of the inverse cosecant of u is -1 over absolute value of u square root of u squared minus 1 times du. Okay, so that, I'm okay with that at this point. And those are your 6 inverse trig functions. So We've gotten 6 trig functions, 6 inverse trig, 2 exponentials, 2 logs, power rule, product rule, quotient rule, chain rule, constant rule, sum and difference rule. Whew, all the rules. Now you can theoretically take the derivative of any algebraic expression I give you, including ones where the rules do not apply, like in the logarithmic one I gave you last class. Okay. Now, just a couple of notes for calculator use. The calculator only does inverse, sine, cosine, and tangent. It won't do secant, cotangent, and cosecant. So there are some things to do. If you wanted to do the inverse secant of some angle in your calculator, if you think about the inverse secant, that's an angle that gives me x over 1. That's the same angle that gives me a cosine of 1 over x. So I would just do the inverse cosine of the reciprocal. So for example, if I wanted to figure out what is the inverse secant of 4, I would just do what is the inverse cosine of 1/4. Okay. Same thing for the other ones. So like cotangent is just the same thing as inverse tangent of 1 over x. Cosecant of x is just inverse sine of 1 over x. So these are how you have to type them in the calculator. And those are the inverse trig functions. So the last thing I wanted to focus on today, and take a break if you need it, because that was like a lot of brain. So if you need to like pause and come back, that's why I'm on the YouTube or in your drive so you can do that. Okay, we are going to talk about inverse functions. So if you remember from years ago, inverse functions are 2 functions where the domain and range are switched. And we've talked about it a little bit. They are reflections of themselves over the line y equals x. We also know that if we have a point A, f of A on the original graph, it'll become f of A, comma A on the inverse graph. Knowing all this, we're going to be investigating what can we say about the slopes of inverse functions. Okay, so let's do an example and see if we can't figure something out. If I wanted to find the inverse function, let's think if we can remember how to do that. We would make it x equals 2y cubed minus 1. And then all I would do from here is I would get y by itself. So x plus 1 equals 2y cubed. X plus 1 over 2 equals y cubed. So y equals the cube root of x plus 1 over 2. Okay, so if I think about 2x cubed minus 1, that's way off the screen. So here is the original function, okay, and then in red I'll do the inverse function. So it'll be 1, 1, negative 1, 0, negative 3, negative 1, and it'll look like this. Okay, and again, it's a reflection over y equals x. So that's the relationship between the 2 functions. Okay. And here we can also see that on the original graph, there was the point 0, comma, negative 1. And on the inverse graph, there is the point negative 1, comma, 0. Okay, which leads us to the next thing. If f of x contains the points a, b, and c, d, then f inverse contains the points b, a, and d, c. Okay. Now let's think about what that would mean for the slope. If we've switched, let's think about the a rock here. F of x's a rock would be d minus b over c minus a. F inverse's a rock would be c minus a over d minus b. Sorry, I almost sneezed. What's the relationship? The rate of changes are reciprocals, not opposite reciprocals, guys. We're not talking perpendicular lines, but they're just reciprocals. So what that means is that if we switch the x's and the y's, then all we're really doing is switching the rise and the run. Well, why that's helpful is that if a function's differentiable, then if we were to like reflect that graph, it would also be differentiable. And if every y is x and every x is y, then the slopes of the tangent will just be the reciprocal of the slopes of the inverse. And so let's kind of like prove that in a using our famous like inverse trig proof. So let's start with the fact that the function of the inverse function of x, if I compose them, it just gives me x. If I find the derivative of this, I would get the derivative of the outside, keep the inside the same, times the derivative of the inside, which I don't know, it's what I'm trying to show, has to equal 1. Their slopes are reciprocals if their product is 1, so the derivative of the inverse function of x is just 1 over f prime of f inverse of x. Okay. So now, if I were to do this, here is one thing that you need to understand. If we have the point a, b on the f function, that means the inverse function would be ba. Okay. So if I want the inverse slope at b, because that is the input on the inverse function, I would have to do 1 over f prime of a, because that is the output. So if you notice, it's f prime of whatever the f inverse of x is. So it's like you have to think, what are the corresponding points and how do I flip them? So let's do a couple examples of this so that you can see and why it's helpful. Now, sometimes you can just find the inverse function and all is well with the world. Sometimes you can't find the inverse function. And when you can't find the inverse function, that's why understanding the relationship between inverses and the regular function slopes is super helpful. So what I would do here is, first of all, if I have the point 3, 9, okay, let's say we want to find f inverse prime at 9. Okay, so by definition, f inverse prime of A or of B is 1 over f prime of A. So this is going to be 1 over f prime of the f inverse of 9. I think this is confusing. So what I have to think is, okay, if f has the point 3, 9, then f inverse has the point 9, 3. So f inverse of 9 would be 3 because the x's and the y's switched, and that would give me 1 over f prime of 3. So if I can figure out what f prime of 3 is, that would be the slope here on this point on f. Is it the slope at 3? We can find the reciprocal of that and get our slope of our inverse graph at 9. So if I want to find f prime of 3, f prime of x is just 2x. F prime of 3 then would just be 6. So this slope on the original graph would be 6, which means our slope would be 1 over 6 for the inverse function. So I set it up like this every single time. What is the point on f? What is the point on f inverse? Okay, what is the slope on f? Now what is the slope of the corresponding point on f inverse? And that helps me because sometimes I don't have like all the information I need, and sometimes I can't like figure out what I'm trying to find, especially when I can't find the inverse. So if you look at this function, there is no way in HE double hockey sticks I'm finding the inverse function. So if I want the inverse function slope at 11, I'm going to do the fact that it's 1 over f prime of f inverse of 11. Okay, so what does that mean? Well, I have to think. There's a point on f and a point on f inverse. I'm plugging 11 into f inverse, which means I would be getting out 11 on f. Now I'm asking you to plug in 3 for a reason. So let's plug in 3 into f and just see what happens. So 3 to the 5th plus 2 times 3 to the 3rd. This is just 3 to the 3rd. That gives me 3 squared plus 2. That's 11. So I have the point 3 comma 11 on my function, which means I have the point on the inverse that's 11 comma 3. So if I want the f inverse slope at 11, I'm going to take 1 over the f function slope at 3 because they are the corresponding points. So now if f of x equals 1/27 of x to the 5th plus 2x cubed, then f prime of x would equal 1/27 of 5x to the 4th plus 6x squared. If I plug in 3, and work that out, I'm going to end up getting 17. So my slope would be 1/17. Technically, what I should have done is set this function equal to 11 and solved it, but I'm not trying to solve that equation either. So let's see if we can do an example where there are no equations, but where they give you a table, because they love a good table here. So given the table below, find g prime of -2 if g of x is the same thing as f inverse. Okay, so if I want g prime of -2, it's going to be 1 over f prime, since they're inverses, of g of -2. Now, sometimes they're going to give you g of -2. In this case, they do. Sometimes they're not. So I'm going to show you both ways to do it. So here, if I plug in g of -2, it's just g of -2 is 5. It's just 1 over f prime of 5. F prime of 5 is 1 over -1/2, so the slope would just be -2. Okay, the other way to think about it, I'm going to think about f and g as two different functions. Now in g, I'm plugging in -2, which means in f, I'd be getting out -2. So I'm looking at my f values and saying, where does it equal -2? Well, that's at 5. So I know those points, -2 comma 5 and 5, -2. So if I find f prime of 5, I get -1/2, which means g prime of -2 is just the reciprocal of that, so -2. So either thinking about it as the two corresponding points, or understanding that it's f prime of whatever you get when you plug -2 into the function, both ways will get you the answer. This is a marination one. We'll probably have to go over it a few more times, but you'll have a couple to practice for homework. And that, my darlings, is all I got for day 5.